Welcome. In this lecture, we're going to resume our discussion and we will continue with dispersion and refraction. So I will use the homework which I assigned in the previous lecture as our starting point. So the homework review will connect our previous discussion with the upcoming discussion. Remember, in that homework, you were supposed to calculate the angle of refraction for two different scenarios, for two different lights, or rather light rays of different wavelengths, and compare how these angles of refraction relate to one another, and come up with some kind of a conclusion. So we will first go through that and then arrive at some conclusion, and even more general conclusion. And then this will allow us to begin to talk about lenses, which is a preface to discussing image formation. Okay, when we come to lenses, for this lecture, to prevent it being too long, we're going to first talk about the types of lenses, which are kind of like the most basic kind. And then we're going to set up the necessary terminology which will make it easy for us to transition to image formation by lenses. Okay, first things first, let's look at the homework. In the homework, you were given a scenario where two light beams, both incident to diamond, coming from the vacuum, and they're incident to diamond at an angle of 23 degrees. The one light is orange light, hence it has a different wavelength, while the other one is blue, hence it has a shorter wavelength. Remember, orange light has a longer wavelength, while blue light has a shorter wavelength. And by using the supplied information in our previous lecture, we could determine what the angle of refraction would be when the light beam, an orange light beam, propagates from the vacuum to the diamond, or to diamond. And when we plugged in the numbers, what we obtained was that the angle of refraction for the orange light is 9.3110 degrees. And performing the same calculation for blue light, we would obtain that when blue light moves from a vacuum to a diamond medium, at an angle, well, if its incident angle is 23 degrees, you'll find that its angle of refraction will be 9.1995. Notice that the orange light has a larger angle of refraction than does blue light. Let's go on to the second one. This is a good data point for us. Let's go on to the second one to see if this is true. Generally. Okay, the second situation was where the light beams were no longer moving from a vacuum, but this time they were moving from a polystyrene to diamond. This time around, the angle of incidence is 17 degrees. And again, performing the same calculation, we found that for orange light, the angle of refraction was given by 10.392 degrees. It's worth mentioning that the index of refraction for polystyrene as experienced by orange light is different from that experienced by blue light. The point is N1 for the orange light is going to be 1.490, whilst for blue light it's going to be 1.499. And the same goes for diamond, because orange light interacts with the medium differently compared to blue light. Remember, that's why we have different indices of refraction. It has to do with how strongly does the light interact with the atoms of the medium. Okay. When the dust settles, after computing these, we find that the angle of refraction for the orange light is 10.392 degrees Celsius, degrees, not Celsius, degrees, while blue light is 10.33. Notice, again, the angle of refraction for the orange light is larger than that of the blue light. And this was true initially. We noticed that even for the first situation, the angle of refraction for orange light was larger than that of blue light. So what kind of conclusion can we arrive at? I'm pretty sure if you attempted this, you would have arrived at some conclusion, but this is how I would phrase it, and that is, for the same angle of incidence and the same media propagation, that is, we're moving from the same medium, we're dealing with two sets of medium, same two sets of medium. For instance, vacuum to diamond, both lights, orange and blue, are experiencing the same propagation. What we have realized is that the orange light will have a larger angle of refraction than blue light. Again, I emphasize that this conclusion arose from the fact that we had the same angle of incidence and the media which were involved were the same kind. Of course, it would not be meaningful if we had blue light go from polystyrene to diamond while we had orange light go from vacuum to diamond. That would not allow us to reach a reasonable conclusion. Okay, so this is what it looks like at face value. The point is, orange light has a larger angle of refraction than blue light. A better way of phrasing this is that orange light refracts away from the normal line. Remember, the normal line is the line perpendicular to the medium at the interface where the two media meet. It's the line perpendicular to those. Let's see. Okay, we didn't draw it here, but I believe you remember what this means. And then blue light refracts toward the normal. That's very, very important. These ideas, this thought of refracting away and refracting toward, is going to be quite useful when we talk about lenses, because this will distinguish one lens from another kind. Where it will have to do with how does that lens affect light? In what direction does it refract it? Would it be away or toward the normal? Okay, so this conclusion was related to different wavelengths of light. Can we do better? Can we attempt to generalize this? Of course, our calculations were based on orange light and blue light and the data we were supplied. Now, suppose we were to just take a generic light beam, think of it as white light. Is there some kind of a conclusion we can arrive at? This is what we're going to go for. We're aiming to have a general statement than this one about orange and blue light. Now, we're going to consider an example. This time around, we're going to compare a transition between two media, but we're going to play it forwards and backwards. What do I mean by that? What I mean is we're going to consider a propagation from vacuum to water and also consider the propagation from water to vacuum when we keep the angle of incidence fixed. Okay, here goes nothing. Let's consider first the situation where we have the propagation from the vacuum to water. So the blue shade here will represent our water, whilst the clear side will represent our vacuum. We begin with an angle of incidence of 30 degrees. And of course, because this is a vacuum, we know all light in the vacuum travels at the speed of light, which is the 3.0 times 10 to the power 8. Hence, its index of refraction is equal to 1. So the index of refraction for this medium is 1. Whilst that of water, we know that it's something we could read off of a table, and that is 1.33. Now, in such a transition, in such a propagation where we go from a vacuum to water, what we determine is that the angle of refraction is 22.030 degrees. Suppose we were to play the exact same backward, that is, now we're considering a transition not from vacuum to water, but this time from water to vacuum. What would the angle of refraction compare? How would it look? Okay, well, we have enough data to compute that. Notice here our angle of incidence is fixed at 30 degrees, and our medium, our source medium, we know its index of refraction is 1.333, whilst our destination medium is the vacuum, which has an index of refraction 1. So then again, we go through the same calculation. We find that the angle of refraction when we go from water to the vacuum is going to be 41. Again, notice this. The angle of refraction when we are moving from vacuum to water is a lot smaller than when we're going from water to the vacuum. Can we generalize this statement? Can we say it in a more general sense? Well, that's exactly the purpose of the next slide. We note here that light refracts away from the normal when it propagates into a medium with a smaller index of refraction. Light propagates away from the normal when it's moving into a medium with a smaller index of refraction. What do I mean by that? Let's go back to our diagram. The index of refraction of water here is 1.333, whilst that of the vacuum is 1. So in this situation, we are propagating from a medium with a large index of refraction to a medium with a smaller index of refraction. The point is the destination medium has a smaller index of refraction than the source medium. Notice our angle of refraction is a lot larger, hence the light is refracted away from the normal. I hope this clarifies what this first bullet point means. Now, what about the other situation when we are moving from a medium with a small index of refraction to one with a larger one? Well, as you probably might expect, we see that light refracts toward the normal. It probably is wise that I also highlight this and change color to make sure that it catches your attention. The point is that light would refract toward the normal. Hence, the angle of refraction will be smaller whenever a light beam is propagating into a medium with a larger index of refraction. These two statements become key when we want to manipulate light to our advantage. This enables us to change the direction of light for certain purposes that serve whatever goal we would like to achieve. Actually, at the core of it all, the discussion on lenses hinges on these two ideas. If you would like to understand how lenses work, these two statements are critical. We need to understand how light will behave when it changes media with different indices of refraction. Okay. Now we're in a good position to start to talk about lenses. Although lenses are something that are things that are familiar to us, I would like to attempt to give a definition, a very loose one. It's that lenses are optical instruments, typically made from transparent materials, but the key is that these materials are capable of refracting light. That's key. It's that they are they have the capacity to refract, hence change the direction of light. Typically, these materials or these instruments are found in, probably you should be familiar with this, cameras on your phones, cameras on your phones rather, in your eyeglasses, binoculars, microscopes, all kinds of optical devices probably. And the two types of basic lenses we're going to focus on are the converging lens, also known as a convex lens, and the other kind is the diverging lens, also known as the concave. These lenses acquired their names, or they've been assigned these names by virtue of how they change the direction of light. I think converging and diverging are quite telling of how these two lenses manipulate light. Well, a converging lens causes parallel incoming rays to converge to some one singular point. All the light rays that are parallel to one another and they are incident to this lens, we will find that if the lens is a converging type, we will find that this lens will tend to change the direction of all those light rays so that they head toward one point when they exit the lens. This statement will be clearer when we talk about how a converging lens works. And again, by the name, a diverging lens would probably, I guess you probably have figured this out, that diverging lens will cause parallel incident rays to, instead of converge, but rather diverge or scatter. The scattering of these parallel incident rays will be such that will seem as though they have diverged from one point. Again, this statement will also be made clear when we talk about how diverging lenses work. Okay, so now I've made so much progress without selecting one particular lens, so now it's time we begin to make things a lot more specific. So we will begin with the converging lens. As promised, that a converging lens takes parallel light rays, and the simplest or the three exemplary parallel light rays we're going to focus on usually are this one, and this one. Notice when the light rays enter this lens, I should say that this is our lens, this device here. When they enter this lens, they get the direction of propagation gets changed, so that this ray here changes its direction to that way, whilst this one changes its direction this way, and this one maintains its direction of propagation. And the key here is that they converge to one point. They converge to one point. This point is very significant. It's actually a feature of the lens. It's known as the focal point. All these parallel light rays will be converging toward this point known as the focal point. The distance from the focal point to the center, the vertical center of our lens, is known as the focal length. It's known as a focal length, usually typified by a subscript or a scripted f, lowercase scripted f. Please don't confuse this with frequency. I think in the context of optics, it's safe to say that the scripted f will correspond to focal length. And in the case where there's confusion, more info will be supplied so that we disambiguate between focal length and frequency. Another important term that we're going to have to get used to, in addition to focal point and focal length, is this one known as the principal axis. Some books refer to this as simply the axis. The principal axis is the middle line that cuts through our lens. That is cuts through our lens equally. That is, the top and the bottom parts are equal. So that central line is known as the axis. Sometimes some books call it principal axis, sometimes they call it axis. Don't be confused, they all refer to the same thing. This middle line is known as the axis or principal axis. And here's the key again: a converging lens will always take incoming parallel light rays and bend them, and bend in quotes, or change their direction so that they meet at some common point known as the focal point, and this focal point will be on the principal axis. Hopefully this discussion makes that initial definition of a converging lens a lot more clear. It is important to note that a converging lens may not cause all the light rays incident to it to converge to this point, but it will always do so for parallel incoming. For instance, there's no promise how the lens will treat light rays that are coming in like this. These two light rays may not converge to the same point because, well, they're not parallel to begin with. But a converging lens will always take parallel incoming rays and cause them to converge to one point on the exit, on the other side of the lens. Okay. Now, how do converging lenses work? Actually, the story of converging lenses, of lenses for that matter, has to do with Snell's law. We know how light behaves when it travels from one medium to another when the two media have different indices of refraction. Particularly, we might consider our lens made out of some material, and that material has an index of refraction larger than that of a vacuum or air. What we do know is we're going to focus on one light ray. Here's a light ray coming in. When this light ray comes in, because the index of refraction here is larger than this source, so the light ray is entering our lens, a lens made out of a material with an index of refraction N2, which N2 is larger than N1. Remember our rules, is that when a light ray enters a medium with a larger index of refraction, it will bend toward the normal. Because of our lens has a curved surface, our normal here is going to be this line on that front surface, this line. So over here we have an incoming light ray, and it's going to get bent, or its change of direction will be toward the normal line. So we get light bending toward the normal line. Now, what about this interface when it gets to the back face of the lens? A light ray is coming, gets to this interface where the light ray is about to go from our lens to, let's say, air or the vacuum. But the key here is that the indices of refraction are compared this way. That is, the index of refraction of the material is larger than that of the air or vacuum. Now, what did our rule about the indices of refraction instruct us? When we're going from a material with a larger index of refraction to a material with a smaller index of refraction, the light ray will bend away from the normal. Again, by virtue of the curved surface, our normal line looks like this. Now, if we want to bend away from the surface or from the normal, our light ray will take this path. And it is by this process, which is nothing more than Snell's law, that a converging lens bends light toward the focal point. Actually, the focal point of the lens is related to this curvature here. We will talk about it later. Right now, it's just to connect the law of refraction to lenses. The point is, lenses are simply exploiting the law we have been working with thus far. Okay. Now we can move on to diverging lenses. Diverging lenses, as I've mentioned earlier, they scatter light as though the light was coming from the same point. Over here we have a picture of this. I should say a diverging lens scatters parallel incoming rays and it scatters them as such that they look like they came from one singular source. As you can see over here, this light ray is scattered, rather its direction of motion is changed such that it moves that way, and the lower one also this way, and the middle one is kept in its path of, or in its line of direction. It's not affected. You can test this all the time. This is always true. That light rays that are perpendicular to the surface of a lens will not be deflected. They will keep their line of direction. That will be a good homework for you to try it out. You will see that if the angle of incidence is 0, the angle of refraction must also be 0. Okay, that's beside the point. What is true of diverging lenses, as was for converging lenses, is that they also have a principal axis, and again, it's this middle line that would cut the lens equally into equal parts, the upper part and the lower part. And also, diverging lenses do have a focal point, and that focal point is located here. It is this point that these light rays seem to have been scattered from. This focal point, when these light rays are diverted, it would seem like they issued from this point. So the focal point for diverging lenses become the point of divergence, whilst for converging lenses is the point of convergence. That's one way to think about it. Okay, and again, the distance from the focal point to the central axis of the lens is known as the focal length. Now, again, we can talk about how diverging lenses work. Actually, it's the exact same principle. Again, it's Snell's law in action. Let's consider the upper light ray. That is, we're going to focus on this one. Of course, the same argument follows through for the third light ray, but we're going to focus on the one, and hopefully this will give us an idea of how this works. So we have our incoming light ray. It's incident to the surface of our lens, but look at our surface, it's curved. So the normal to this surface is over here. That's the normal line. Again, our lens has an index of refraction, we call it N2, but N2 is larger than N1. So that is, we had our medium over here whose index of refraction was N1, but our lens is made out of a material with an index of refraction N2, which is larger than N1. What do we know about such a propagation? We know that when light enters or propagates to a medium with a larger index of refraction, it will bend toward the normal. And you will see that light ray here is bending toward the normal. The point is this angle here is smaller than this one here. And then the light ray will maintain this path, this line of propagation until it reaches this surface where it's about to exit the lens back into, let's say, the vacuum or the A. But because this part of the surface is again curved, unlike what we have been dealing with, which has been flat, but this one is curved, our normal line again is going to be like this. Remember, the normal line is the line perpendicular to the surface or to the interface of the two media. So this is our normal line. But when light exits the lens to enter the vacuum or the A, it's going from a medium with a larger index of refraction to a medium with a smaller index of refraction. What did we learn about that? We learned that a light beam, which is undergoing such a propagation, will bend away from the normal. Well, our normal line is over here. Therefore, the light beam will bend away, which means this angle of refraction will be much larger than the angle of incidence in there. Hence, you might notice that the overall change of direction was one of diverging. They came in parallel, or rather they came in horizontally, but now they are, well, this upper light ray is moving away from the horizontal line. You might imagine that this same idea holds, but for the lower part of the lens, you might notice that in such a situation, let me append, let's say this was our lens. You might imagine that our light ray would have done something similar, something like this. So this would have been, of course this is not drawn to scale, but the point is to demonstrate is that the light rays, although they come in parallel, they exit diverging. And the thought is that the way they diverge as though they came from the same point. And that point would have been the focal point of this lens. Okay, in order to avoid this lecture from being long, I will stop here. But so far we have enough information to begin to talk about image formation. For further reference or for further reading, I commend you to look at OpenStack's College Physics, section 25.6, to fill in any gaps anything that you may not understand at this point. And after this, we're going to talk about image formation. Thank you.